Like I said, if you have to leave early today, that's fine. But I'm gonna stay on and just really kind of power through this because it's not that many sections left. I could make this all make sense at the end, but I want to really finish this today so we could really start off April in that new kind of 3 units of 5, 6, 7, where we start talking about the trends within the law of conservation and how that relates to the last part of what we understand about, orbits. So that if we can get to 7, it'll be orbits to where it brings everything in home together to where you see about orbits, solar system, everything to where we start seeing about how the stuff we talked about in the first unit relates to a lot of things we see in nature. So we're almost there. So we just got to introduce those laws of conservation in 5 and 6, and then we can have a full view of everything. So let's finish this today, right? And so really, this was still forced in 2 dimensions, right? And I think we did all of this was just regular vector addition, right? So we got to be able to see like the vectors. And this stuff is like all review familiar, right? But as once we started getting into like adding the different forces, right? By finding their components, that we started to see this trend in talking about, equilibrium states, right? So we talked about Newton's laws. First law, object in motion stays in motion, except affected by, unless it's affected by a unbalanced force. Newton's second law, if the force is unbalanced, then the sum of the forces is equal to mass times the acceleration. And we're talking about those 2 laws, right? We can use vector components to analyze the situations, but really when we see about equilibrium states, we wanted to understand what constitutes as being in equilibrium, right? Remember, sometimes some things could be happening and that doesn't always mean that the object is at equilibrium. Like if an object is at rest, that always doesn't mean that the object is at equilibrium. But if we go the other way around, if an object is at equilibrium, sorry, if an object is at rest and is at equilibrium, but if an object is at equilibrium, it doesn't mean it's at rest. That's what I meant to say. Give me 1 second. And I believe we went through all of these. We talked about the truths and false. We took our time going through these statements, right? Now, we stopped here. Once we started to really understand the difference in the equilibrium states around and establish like what we meant by that, right? We started looking at forces, right, based on the force free body diagram. We were able to conclude looking at this, right? The forces on the up, the vertical, like F1 and F2y, were equal to each other just because we see like the length of the arrows and the magnitude, right? Sorry, the x's were equal to each other. Then we looked over and we compared F1y, the vertical, to F3, which is below it, right? And you can obviously see that F3 is a little bit bigger, right? So then we compared that. Same thing with F2, it's a little bigger, right? But then we concluded that summing those individual forces on the top will equal to the individual forces on the bottom, which would be F3. So F1 plus F2y added together will be about the same as F3y, right? And that will be able to create an equilibrium state to where all the forces are balanced. Now, think about an application where we will want the forces to be balanced in that way to create an equilibrium state, like an actual application. A plane cruising. Now, that was good, but I want a really simple one because it'll go right into our next problem. And it's literally all around this room. Look around the room. Give me something in this room that's at rest. A chair. Or even better, what's on the walls?
Pictures.
Pictures, signs. How is this clock up here?
Hanging on a string. A nail.
Yes, it is. Uh, I'm trying to get it off, but you can't see it. But it's hanging on this, right? So, taking advantage of that, right? This technically is an equilibrium state. This weight of this clock is going down, being pulled by the force due to gravity, right? That's just weight. but then we have something in the back to be able to hold it up. Now, you can't see this. Oh, it's a nail back there, right? But what is it hanging off of? What's holding it up on that nail?
It's like a
Little
groove that's in the back of your body.
or a string. So it's a string to where it hangs off of it, right? So with a string that hangs off of it, we create what? What type of force to counteract? Gravity. Say it louder. Tension. Now we have a tension force, right? Torque is when you look at angular motion, so like turning something. So how much something would like turn, stretch that, like, or like this, like turn this, or like if I'm trying to rotate, like hit something. Yes, that's torque. We'll talk about that too. But no, tension is a string. Well, sorry. I'll get back to you. I'll get back to you. Yes. So now with that, right? The simplest equilibrium state that we'll cover right now is the start of our work today, right? Hanging a sign. So we want to know what would be the best way to hang a sign so that it can stay and have the longest lifetime, which would be it would just never move, just like that clock, right? We don't want it to fall down. Now think about it, right? When you're trying to hold a sign, you know it weighs a certain amount, right? And by you having the string, right, you want to position the string to where it's a little bit even, right? Because you don't want it to hang on one side and be off, or you don't want it to be longer on one side, because then you'll create what? An unbalanced amount of force. And so then that'll cause what to happen? Over time. If it's unbalanced and you put too much stress on the string, what will happen? It'll break. And then what'll happen to the sign? It'll fall down. So you want to avoid that, right? So here's a real world scenario where we're like, what angle should we position our strings at, right? And I say strings because in this scenario, we're going to use two strings. So we're going to use two strings of equal length, and we're going to have them at equal angle, right? But we want to see how we could position them to get the best angle. Okay? So we have our strings right now, and what we want to do is calculate the tension at each sign. And then once we see the tension at each sign, we want to see which one has the safest arrangement. This is a very simple problem. And I want us to put all together everything that we did before, but also use as little math as possible. So let's use teamwork. Tell me if you can see the board. Hold on. Can we see the board?
Yes.
Hold on. Is that clear?
Yes.
That's clear.
Is it clear? Better or worse? The same or better or worse?
That's a little better.
Okay. So I got my sign at 3 positions, right? And how I'm gonna represent these positions is exactly just like how they have this picture, right? So if I have the first one here, 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 here's my free body diagram. I got it at 15 degrees, right? Actually, let me do that. I'm gonna do the free body diagram for each one. And then I'll extract the triangles from it. So on each string, right, we have some type of wire that has an equal tension. Correct? Then what do we have going down?
Gravity.
Gravity is weight. Force due to gravity, right? Force due to gravity, right? Each scenario. Now, what's different in each scenario is the angle that we operate at. Now, for this one, I'm gonna make each angle. I should have used black. Yeah, I'll still do it this way. I'll use angle and do an opposite color. All right. So this one's 15. This one's 15. Next one is 45, right?
Yes.
45. 45. Last one, 60,
Yes.
right? Now, intuitively, right? The strings are going to be different lengths or the same length.
Sorry.
Same lengths. So if they're the same length, they have the same amount of tension, force for them, right? So if I want to find the tension force, I really only need to find the tension force in how many strings. Both of them are just one, because it'd just be half of whatever the gravity, right? Now, why did I say that? Because when we do the free body diagram, when we do the calculations, right? We want the forces to be unbalanced or balanced. Balanced. So that means the sum of the forces must be equal to, if the forces are balanced, the sum of the forces must be equal to equilibrium. Balance forces. We got two ways. Which one would I pick? Is the sum of the forces equal to 0 for equilibrium force, or is the sum of forces equal to mass times acceleration if they're balanced? I'll give you a hint. The object stays in motion. The object in motion stays in motion unless acted upon it by unbalanced force. That's Newton's what law? First, second, third. First law. So when the forces are balanced, the sum of the equilibrium state, right? So that means the sum of the forces is equal to 0. So which one would I use? This one or this one? The first one. So this is Newton's first law, right? So this is when we have balanced forces. This is unbalanced. But let's come back over here, right? So we're in an equilibrium state, so we want balanced forces, right? Now, with us wanting balanced forces, what does that really mean? Whatever is now in my y, right? I want whatever in my y, I'm going to do my y to equal 0. That means my up must be equal to my down. So now, I want to make sure that my F grav, which is down, right, is equal to my tension force. Well, I have two tension force, right? So I have 2Ft equals F grav. So I have the two tension from the strings. That must be equal to my F gravity. And more specifically, what component? The Y component. Because we're talking vertical, right? We don't care so much about the horizontal. We care about the vertical. So now each time, for each scenario, we want to find out what is this part. Because this part has to be equal to F grav. Ty, Ty. Right? So the vertical part from each one has to be able to hold the weight. Now, what we just said, how many vertical components do we have for tension? We have 2. So now if I just want to find out what FTY is, I would have to do what? IC. Yes, because IC. Yes. Times 2, so I divide by 2. So I divide by 2 here, divide by 2 here. Now I know that the tension Y component is equal to half of whatever my weight is. Right? It should be equal to half of whatever my weight is, right? Sorry, just blank for a second. So now, what else can I do? Now, each one of these scenarios, right? I can figure out what, and they might have already did it. Yeah, they already did it. So I'll just keep explaining it. How much that Y component really would be, right? Because all I need to figure out now is, what is my weight? How do I figure out my weight? Let's see if they give it to us. Oh, they kind of give it to us already. So they said that each sine weighs about 10 newtons. So now if I institute that in there right there, right? Instead of it just being F graph, now I know that this is equal to 10. So now, see, Y is equal to 10. So my weight is 10 newtons. So now I know that my vertical component for each string is going to be equal to what? If I know that my total is 10 newtons for my weight and my vertical component, I just need to get one of them. I divide 10 by 2 and I get 5. Now this part they gave you, but this is how they got the 5. They said I just need to figure out one of these because both of these two are going to hold it up, right? Now what does that do, right? So in each scenario, I can now change one of these to, I'll just change one of them to 5, right? So now this is 5 newtons. I know this is 5 newtons. Five newtons. So now in each scenario, right, we have the same vertical components. But what's going to change is based off our angle, the horizontal components, which then in turn will change how we look at our overall tension. And that's because of we changing the angle, right? So if we have 15 degrees, it'll be a little bit flatter, right? Now if I'm at 45, it'll be a little bit more steeper. Then if I'm at 60, it'll be a little more steeper. So now we want to see how that affects the actual value that we have here. Now, how can we do that? In each scenario now, we can pull out each one of these and make these individual triangles. When we start treating these vectors like forces or like triangles, now we can actually be able to use what we've seen with trig to be able to pull it out and find out the tension value. So let's pull this one out, right? So now I'm here. My tension is what I'm trying to find. I have my vertical component and I have an angle. Now, if I was trying to find this one, right? Yeah, we'll do this one. I would use one of the 4 trig functions that I had established over here. We got sine, the angle is equal to opposite over hypotenuse. Cosine of the angle is equal to adjacent over hypotenuse. Sine of the tangent of the angle is equal to opposite over adjacent. In a triangle that's right, and it looks something like this. I said this is the angle, right? This would be opposite. This is hypotenuse, and this is adjacent. So now, based off of having this triangle, based off of having these equations, if I wanted to find the tension force off of what I have, which one of these would I use? Say louder. The first one, which is sine. So let's use sine, right? So I'm gonna start off rewriting my equation. Sine of the angle is equal to opposite over hypotenuse. What is my angle? 15 degrees. So I'll put that here, right? Do I know my opposite? I do. It's 5 newtons. Do I know my hypotenuse? It's going to be the actual tension force. So I'm going to just do a little bit of quick maths, multiply this through. So now I have my tension force times the sine of 15 over 5 newtons. I see multiplication, so I divide by sine of 15. This part is math. So if I got the sine of 15, then I take that and divide 5 by that. So let me do that. 5 divided by, hold on. Did anybody do it?
7.69.
Say what you got one more time.
7.69.
Sorry, you're doing 45?
15.
Oh, I got 19.3 newtons.
Let me see. That's what I got. Your calculator's in radians.
Oh.
Yes, it is 19.3. I got the same thing. Give me 1 second.
I may have jumped ahead earlier. I put in the answer to the question in the chat.
Oh, that's fine. There we go. There you go.
Oh, thank you.
All right. So now we're here, right? And we got this equal to 19.3 newtons. So now I can re-put this up here that I know that this tension force up here is going to be equal to 19.3 newtons. Now the goal that we want to do is to be able to compare this same way here for this one and for this one. I am spending a lot of time on this problem, but now this is the part where we want to be intuitive. Let's do less math as possible, right? So now we're here. Same type of triangle. This is still 5 newtons. This is still my F tension. But what changes? The angle. Same thing here. We're doing the same calculation. 5 newtons. These are all right, too. The angle. Now, this is where you stop. Don't grab your calculator. Use the tricks that I gave you. If this angle is 45, what is this angle going to be? 45. Now, what type of triangle is this? Right triangle, but what type of right triangle? Remember the special right triangles? Right. This is a
Pythagorean theorem triangle?
we use Pythagorean theorem in all of them, right? But what type of triangle? 45.
Acute.
Hold on. 45, 45, 90. So if these two angles are the same, what does that mean about their sides? These sides are going to be the same. So now we got this one and this one. So they'll both be the same. So technically, this is equal to 5 newtons as well. But really what matters is how can we find this? The 45, 45, 90 triangle, I'll bring it up here. Let me see if I can go back, because I think I can go back all the way to vectors. Right here. So now we know that we have x, and then x root 2. Right? So let's say that this x, which is 5 and 5, so our F tension must be x times root 2. So we can write it as our x tension must be equal to 5 newtons times root 2. We can actually find that. What is 5 times root 2?
7.07.
7.07. I believe that's correct. Round it up, 7.1. See how much faster we were able to do that compared to the first one? 2 seconds. Now we come over here, right? We have 60 degrees and 90. What would this angle be? Say it louder. 30. So now look on the slides. What type of triangle do we have? 30, 60, 90. So I'll draw that one up here, right? Now we have 30, 60, 90. Across from the 30, we have, should be x. Then across from the 60, we have x times square root of 3, right? And then across on the hypotenuse, we have 2x, correct? So now that I know that this is 5 here, right? And it's across from the 60, I want to find out really what this one is, because this one would just be, the tension would just be 2 times x. But we know that this one that's across from the 60 is x times root 3. So now with me knowing that, let me just draw it out so it's not confusing. I have 5 newtons equal to x times root 3. For me to find what x is, I have to divide by root 3. So 5 divided by root 3 is going to go right here. So now let me put it here. 5 newtons divided by root 3, which is equal to how much?
2.9.
2.9. So now that we say this is about 2.9, we know that this now represents x. So now all I have to do is multiply this by 2 to find out what my tension force is. So what's 2.9 times 2? Say it again. 5.8. Now we know this was about 5.8 newtons. The board does look kind of crazy, right? But if you were following me, I hope I did an okay job of trying to break it down to how we get to this problem. And I hope the colors tried up. I really should have used black as my neutral color for all of them and then use blue. But sorry, I wasn't thinking straight. But I wanted you to see how we got from here, which was in unit 3, to now all the way here in unit 4 to doing a problem like this. So we just had to put it all together to figure out how to hang a sign, right? And then we were able to find out the tension force in each one. And it's basically just trigonometry. We just pulling out the triangles, doing some work with it. But the amount of time it took me to get to this point and explain it and go through, did it take the same amount of time to solve these two problems right here? Well, once we've seen that 30, 60, 90 triangle, we were able to do this one in like 2 seconds, and also with the 45, 90. We barely did any math over here. Now, compared to this one, if it's not a nice one, like it's a 15 or like a 23 or something like that, you have to actually calculate it. But it goes to show is, yes, some of these problems might take a little bit of thinking, right? But if you could find shortcuts to be able to do as least amount of math as possible so that you could really focus on the physics, take them. So always be prepared for that part. I know trig could be a lot, but this is where it comes in handy. Now, we just did do a lot of math, right? After the physics. Now we got to come back to the real application. What was the original question that we're trying to figure out? Let's take 2 seconds. What are we trying to do?
Figure out how to hang the picture with the least amount of tension.
Least amount of tension because we don't want the what? Picture to fall because of what happens?
The string break.
The string breaks due to too much tension. So therefore, what are we looking for? The string variation with the least amount of
Tension.
tension. So which one has the least amount of tension?
Third one, yeah.
The third one, right? The least amount of tension right here, which was 5 point. The same in each one, right? They each have 2 strings, but what change each time?
Ankle.
The angle, right? So at this angle of 60 degrees, we make sure that we have the strings have the least amount of
Tension.
tension. So the angle variation is what really created to where we have the tension, change in tension, right? So now that we know that, we actually were able to figure out and do that. I think Peter had already put it in there. It said that this was the answer, but like there's ways that's how we now can change it, test it intuitively, right? So that's pretty much it right there. Yes, it is the same problem. Yes, I did kind of go a little bit long with it, but I wanted to make sure that you actually could fully understand what was going on. But yes, the 60-degree angle will be the best angle for us to hang the hot sign at. So if you're online, take a picture of that real quick. Or if you're in person, just take a picture before I erase it. Good. All right. Now we want to play around with, I think this is level surfaces. Yeah. So this one, right? I'm going to really walk you down to really get you into looking at the different components for level surfaces. So this first one is just a very simple one, kind of easy, right? I think I'm gonna leave this. Let me just do it again. All right. So we just want to calculate the accelerate. I meant to put acceleration for each object, right? So let's start with the first one, right? We're going to use Newton's first law and second law together, right? So in what direction? Let's look at the vertical direction, right? Are my forces balanced in the vertical, up and down? You say yes.
Yes.
Anybody disagree, or we all agree that the force is balanced in vertical? Good. All right. So if my forces are balanced in the vertical, then I can say that the sum of my forces in the y is equal to 0. Let's stop there for a second, right? Let's look at left to right, or x, horizontal. Are my forces balanced in the first one?
No.
No. Therefore, if my forces are unbalanced, then that means I'm going to have what? An
Acceleration.
acceleration. So when there's an unbalanced force, the sum of the forces is equal to mass times acceleration. So that's over here, right? So that means that the sum of my forces in my x is equal to mass times acceleration, right? Now, we want to find out what the acceleration is. So therefore, we need to figure out what is the sum of the forces, the mass, and then go from there, right? Now, do we know the mass of the object? No. So the mass is unknown. But do we know the sum of the forces in the X? What is it? 12 newtons, right? So that's the only force present. So we know we have 12 newtons. We don't know the acceleration, but we know we can find the mass. We want to find the mass. Now, before I do it, does anyone know a way that we can find the mass? How can we find the mass?
You can use the F gravity.
There we go. Have rap, right? Because we know that the sum of our forces is equal to my down. So we have the top, which I believe is a normal force, is equal to F gravity. You don't really have to do all of this, but I'm just doing this. But it's equal to what? 19.6,
Yes.
right? But we know from the previous that gravity, force due to gravity is equal to an object's mass times the acceleration due to gravity. What is the acceleration due to gravity? 9.8. So now if I come over here, right, I know that my force is going to be equal to 19.6. That's what my force due to gravity is. I have a mass, and I have 9.8 meters per second. I see multiplication, so I do division, right? I divide by 9.8, divide by 9.8. What is 19.6 divided by 9.8? 2 exactly, right? Sorry. 2 kilograms equals the mass. So now we have a mass. Now I can take this mass and I can put it over here, right? So now I come here, I got 12 newtons equals 2 kilograms times acceleration. I see multiplication by 2, so I divide by 2. So I divide by 2, and I got 6 meters per second squared for my acceleration. Make sense? All right. Everybody good with this one, right? Now, let me look at this, right? Before I start erasing stuff. We just did this problem for something that looks like this, right? We'll just say apply, right? Don't worry about the numbers, right? That's what the free body diagram looks like, right? For this problem, right? Now, on the second one, what changed?
We added friction.
We added friction, right? Is that friction force bigger than the applied force, or is it less than? Less than, right? But it's present, right? So technically, are my forces still balanced in my vertical? Okay. Are my forces unbalanced in my horizontal still? Okay. Now, what changed out of all these quantities that I would have to change here? If you could kind of see it, explain it.
You have to add on. What is that? Why?
Okay, so we have to add on to what? In what direction? Vertical or horizontal? So in horizontal, we need to change the what? Are you talking about just this one or the whole entire thing? The whole entire thing, right? What do we call the whole entire thing, or all of the sum of the individual forces? Just said the answer. What do we call all of the individual forces added up? The sum of forces, or the net force, right? In what direction? You just said the horizontal, which is also the X. So now we need to change what the net force is, right? So let's introduce the concept of what? Which force is winning? Which one is losing? Which one is winning?
Force apply.
The force applied. So let me put a W here, right? Which one is losing? Which is the L, right? So now I come over here, and before I put this number here, let me establish which one's winning and which one is losing, because that's going to be equal to my mass times acceleration, correct?
Winner minus.
The winner minus the loser. So the force applied was how much?
Hello.
12. So now I got my 12 newtons, right? And I have my loser, which is the what?
Friction.
Friction, which is how much? 8, right? So I have 12 minus 8 newtons equals my mass times acceleration. So now when I come down here, I do everything. And instead of me putting 12, I have to put my difference, which is 12 minus 8, which is how much? 4. So now let me just change this from 12 to 4. Now, technically, did anything else change from the problem? No. So if I was to just change this to 4, would this be okay?
Yes.
So now, instead of me doing 12 divided by 2, I do 4 divided by 2. So now my new acceleration is what? Did I do it right? Now, because it did it right the first time, right? We were able to solve the second problem in like, what, 2 seconds? But wasn't so much calculating and doing math and what they call formula fixation, where you just look at the formulas, you start plugging stuff in. Nah, just take 2 seconds and just look at the picture. The first one, we had no friction. We had nothing going against the applied force. So that's like going on a smooth surface, like some ice, right? We're just sliding. And then now we have friction. So that's like me running on turf. Like I'm stuck in the grass. So I'm trying to run. So now you got a little bit of friction. So now I calculated where there was no friction present, and the only thing that added was friction. So now when we doing that, all I have to do is account for the friction while leaving everything else the same. That's how you be intuitive with some of these problems. So if you could see it visually first, think about it, look at it visually, and then attack the problem, because you can save yourself a whole lot of time to do a simple problem. That's what we're trying to show right here. Now take this, and now we're going to do something very similar, right? Now that was just level surfaces to where it was just flat, right? But now what happens if we introduce the concept of a slanted force, or a force that has a horizontal component and a vertical component? Right? So now we're doing the same thing, but we want to look at it from both situations, right? We want to just basically just fill in the blanks, fill in the missing values for each situation, right? I feel like I skipped something. Did I skip it? Oh yeah, I did. I did skip this one. Yeah. But I could do this real quick, right? So we can make this nice and easy, right? Okay. So I'm gonna redraw this diagram, right? Multiple people said they had to leave at 7. So when it gets to 7, if you got to just dip out, just go ahead. I'm gonna just keep going, but I understand.
Thank you.
So let me go here, no problem. So now I'm gonna go here, right? I'm gonna redraw the free body diagram. We got F graph. What is that? Normal force up top. Yep. And then applied force going at an angle. And that's above the horizon, which is at about 23 degrees. And then F applied is equal to 13, right?
Yes.
F grav is equal to
19 points.
same thing, 19.6. And then norm is equal to 19.6.
There's nothing there.
No normal force? Oh, we don't know what it is. I would have to find it. Okay. I just want to make sure. Yeah, we're going to assume that this is similar to what we had before, right? Now, we don't know what the normal force is, but let's look at this situation. And we see it. It's pretty much like an object sliding, being pushed at an angle. Now, something like this. I was traveling with this eraser like this, right? Am I lifting above the ground? Is the object going up in the air? No. So if the object's not going up in the air, it's connected to the surface. That means that my forces are in the Y. Are they balanced or unbalanced? Balanced. So let's just treat that our Y. The forces are still balanced. So we're here, right? Now, in my X, are the forces balanced or unbalanced? Let's think about it, right? Before I even get there. Let me break this up. You have F applied X and F applied Y, right? So now, are my forces in the horizontal X to unbalanced?
In the end.
Unbalanced, right? Because I just have X applied going to the right. Do I have anything going to the left? No. So now we have this unbalanced. So we can actually say similar to the other problems where we have the sum of my forces in my X equal to mass times acceleration. Now right here, right? Let's look at this real quick. I could pull this whole thing out and now I have a vector triangle, right? This is 13. This is 23. I need to find out what my Y is, what my X is. Now, real quick, I'm going to do the math to prove it. Anybody want to take a wild guess at what type of triangle that is?
5, 12, 13.
Is that 12, 13, something?
Yep.
5.
Yeah, the fives up here. 5, 12, 13. Right? Now, I know it's a 5, 12, 13, but let me just prove it, right? I'm going to do sine to find this 5, right? Sine of an angle equal to opposite hypotenuse. Sine of 23 is equal to opposite over 13. So now do 13 times the sine of 23. What's 13 times the sine of 23?
5.1.
You already did it? 5.1. So about 5. So you can say this is 5. Now, if I really wanted to, if I say this is about 5, I could either do cosine or I could do, right? I know that this one is 13, 5, and I want to find out what A is, right? You got 25, 169. So I just do here, and I get A squared is equal to 144. Take the square root. What's the square root of 144? So now I know this is a 5, 12 triangle, 5, 12, 13 triangle. So with it being a 5, 12, 13 triangle, now I can actually put these values in here and I have them ready to go. Now I know this is 5 newtons here, and then now I know this is 12 newtons. So now when we're looking at it here, I can now really solve this problem in the same way that we did before, right? So let's look at the over here. We still want to find, let's say, this acceleration, right? What is the sum of the forces in my x now? Just in my x.
Oh.
12 newtons, right? Do we know our mass? Did they tell us?
No.
Nope. So we got to do the same thing, right? We have to find our mass to be able to find our acceleration. How can we find our mass? What was it that we used before? F grav equals? Huh?
Oh, no.
Gravity is equal to, the acceleration due to gravity is equal to, but the weight of an object is equal to its
Mass.
times
Gravity.
gravity. So mass times gravity, right? So now if I know that, I can come over here, right? How much is this object's weight due to gravity? Power force due to gravity is what? 19.6. So now I can do 19.6 like I did before, equals mass times 9.8 meters per second. I see multiplication. So I do division. Divide by 9.8, divide by 9.8. You said this was 2, right?
Yes.
So it's still 2 kilograms, right? So now I could take that, put that over here. C multiplication, do division, divide by 2, divide by 2. Still got 6, right? Yeah. Now, when we think about it, right? We were able to find 6 right here, the same acceleration. So now we want to figure out, we don't know what the normal force is, right? Now, what's different between this problem and the last problem? Remember, last problem we did sum of the forces, up equals down, and we had the normal force is equal to F grav, right? So then they were both just 19.6 equals 19.6 and stuff, right? That makes sense, right? But now my up is still equal to my down, and I have my down is still F gravity. But what's different now with my normal force or my up part? What's different between my up and my down?
There's a extra y component.
There's an extra y component, which is what?
5.
5, or this F applied y, right? Now we know that this value is actually equal to 5 newtons. So you got 5 plus F norm is equal to F gravity, which we said is 19.6. So to find out what F norm is, what do we have to do? Subtract, because I see addition, so I must subtract, do subtraction. 5n, 5n. So now I have my F norm is equal to 19.6 minus 5, which is
14.
14.6. I'm pretty sure that covered everything. We found Fy, which is 5, Fx, which is about 12, and then the acceleration, which is about 6. So then the sum of the forces is about how much? 2. It was, what was the sum of the forces in the x?
12.
12. So that's all the ones for the blank, right? All right. So now let's look at the bottom one and see where it differs at before we start plugging in things. Somebody tell me what differs in the bottom one. Have a good night.
There's friction.
So now we have friction, right? And how much?
8.
friction, 8 newtons. So out of all the things that we just changed, right? So all the things we just did, what is going to change? One more time from the top. Now we have a what? A loser. Because this one is how much? 12. This one is
8.
so therefore, is this one bigger than this one? So this one is my, and then my friction will be my. So now let me come back over here, right? Winner minus loser equals mass and acceleration. So for my loser, I'll put 8 newtons because it's friction. My winner, I put 12 newtons. What does that do to my problem? I got 12 minus 8, which is
4.
So do I put this 12 here? What do I change that to?
4.
4. Because I added friction, so now it affects my force because the actual force going in the opposite direction. So I come here, here. Now I have a total net force of 4 instead of 12. So when I divide by 2, my acceleration now becomes 2. Did anything else change? So I'm good. Does that make sense? Do my numbers match up? What's on the board? Because I just rounded into 12. It's really like 11.97, and then it's 5.01, 08. Those are the actual numbers. But I just did 3, 12, 13, 12, and 5. Yes, take a picture of it. All right. Now the first one we actually calculated. If we would have did the previous exercise, like when you do the practice problems by yourself, you'll see in the exercise right before it, it shows you calculating the 5, 12, 13 triangle. So then when you look at the next one, you should see it automatically, so you shouldn't calculate it. So I had to just do that real quick because I skipped that one when I was doing the slides. But really is that. We get in here, we see how the forces are being applied, but then you would intuitively want to see, oh, wait, this looked like a special triangle, and you play around with it. So now you're not doing as much math, right? So where now you can see it intuitively right here, right? But then when we did to the second one, we changed how we did adding the extra force, which was friction. All we had to do is just change our net force, because that's the only thing we added. And then we just do a simple calculation. So once again, the reason why I'm doing it like this is so that way you can be able to at least see what's going on and see the changes, so you don't get caught up in all the math. Like the math is very much important, yes, but like sometimes it don't even require all of that. It's just a quick look at this next problem that I want us to go through, right? I really want you to talk more than I want you to do math. We're actually making good time. So this one requires us to speak. So we have an applied force of 30 degrees to the horizon, right? And 50 newtons applied force of 30 degrees to the horizon, right? And accelerates a 10-kilogram box across the horizontal sheet of ice. So Ben, Don, and Warren are discussing the problem, right? Ben suggests that the normal force is 50 newtons, right? Don suggests that the normal force in the diagram is 75 newtons. Warren suggests that the normal force is 100 newtons. All three answers seem reasonable, but only one is correct. Which is the correct normal force? And then we want to see what the error is, and we talk about the error, right? So right now, let's do a set of hands, right? I want you to raise your hand if you think Ben is correct and the normal force is 50 newtons. Actually, wait, let me give you 30 seconds to think on your own before you answer. Starting now. Take 30 seconds to just think on your own, come up with your own answer. All right, that was 45 seconds. Okay. Now we're going to go through each one. And Ben, if you think Ben is correct, I want you, actually, let's do this. Write in the chat who you think is correct. Everybody write in the chat instead of me doing raising hands. And I'll just tally it that way. We have 3 choices. We got Ben, Don, Warren. So everyone write in the chat who you think is correct. It's 11 people, so I should see 11 responses. All right, I need 10 more. Oh, wait, it wouldn't be 10 because it's me. Technically 8. 8 more. And it's okay to be wrong. So I'm about to go through it. I got 2 for Ben. One, 2, 3, 4 for Ben. Oh, and it's not quantum. We can't do in between 50 or 75. Pick one. You're fine. Ask me is floating between answers. I need her to pick one so I can measure it. Which one? I got 5 for Ben. 75. Okay, so she picked Don. So we got 1, 2, 3, 4 for Ben. We got 6 for Ben. I got Warren back, Ben. I'm sorry, Wayne. I'm not. What is it? 6 for Ben. Yeah, 6 for Ben. 1 for Don. All right. I'll stop with there. That's a good variation. Now, I want some input because I want us to talk more about this. Why did y'all pick Ben or Don?
I mean, I just looked at the line.
You just looked at it, was intuitively just like,
I looked at the line. I see the one going down.
Mhm.
So it can't be that one. You can say 100 or like 35. 75. You know, it can't be. I moved those out. So the one that's like shortest, I guess.
okay. Anybody else for why you picked Ben?
I think when you go to make the y-axis forces equal, I think 75 and 100 are going to be too much when you add it to the extra y force from your triangle.
Okay. Anybody else for Ben? Anything different? Lakshmi, you want to come off mute? Talk about why you picked 75 for Don?
I was, we just have to find out the y component first, right? So if we do the sine for the 30 and use 50 as the hypotenuse, then the y component comes out to 25. So based on the other problem that we did, wouldn't the normal force be F grav minus the y component of the applied force? So 100 minus 25.
I think you're on to something. Now let's look at it up here, right? Sorry. Back here, right? So if I redraw the situation of what's going on, right? It's basically the same as what we had before. We got this time though, we can actually measure it. So you look at it. Here's the surface, right? And we got the object on the surface. It has a weight and it has a normal force. So we can assume that it's attached to the surface, kind of sliding across just like regular. But it's being pushed now with an applied force above the horizon. What does that mean? At an angle. That angle is 30 degrees. And this entire applied force is equal to 50. Oh, I lied. This is not frictionless. This is frictionless. So it's no friction. No friction. You know this is 100, and you want to find out what is the normal force. Now, based off of this diagram, we got some x components and we got some y components. Let's start with the y again. The sum of my are my forces in my y up and down, balanced or unbalanced? Up and down. Balance. So I could say some of my forces in my y is equal to 0. Now, are some of my forces in my x balanced or unbalanced? Unbalanced. So I can say this one right here again. Some of my forces in my x equal to mass acceleration. See this trying to trend with these problems, especially ones where it's like moving across and sliding. They're all looking similar. So now we come over here, right? What is the sum of the forces in my x? Apply x, F applied y. But wait, before we do this, what does this look like?
Factor 69.
This is x. This is 2x. This is x root 3, right? If I know that this one is a Ross 30 is my y, but I know this is equal to 50, then I know that, yes, this one is equal to what? We actually, do we need this one? We do. So now I know this is 25, so this is equal to 25 times root 3. Now we know that this is 25, this is 25 times root 3. All right? So now, what is the sum of my forces in my x actually equal to?
(25√3).
25 root 3, or how much?
43.3.
43.3.
But we don't need that for the problem, right?
You don't, you just, well, I'm just actually go through it. Right? So now we're here, right? We got this mass, acceleration, blah, 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 blah. We could find acceleration, we could do all that, right? Cool. But we're just trying to figure out what the normal force is, right? But we know the normal force is here is 25. Sorry, we don't know the normal force is 25. We know that the y component here is 25, right? Remember we said earlier, the sum of the forces, that means my up is equal to my down. So if I split this, right? Here's my up part, here's my down part. In my down, I have F gravity, right? Now, what forces do I have in my up? I have norm, and what else?
The Y component.
The Y component. We know that my gravity, force due to gravity, is 100 newtons. We don't know our F normal force, but we know that the F applied is 25. So if I want to find out how much my norm is, I see addition, so I must do
Subtraction.
So now that we know the normal force is actually equal to 75. So who was right? Don was right. Now, what can we really take away from all of this, right? Get out the math and let's think about what we see. To figure out, when we have some type of diagonal type of force being applied, right? That has an X and Y component. When we are talking about keeping our forces balanced, we have to consider all the components, individual components. So when we have a vertical or Y component because we're pushing an angle, that also attributes to how much the normal force is going to be. Because both of these vertical components must be equal to the force due to gravity. So that's why if you're pushing at a different angle, you will change the normal force that the object is feeling. So when we have a different multiple vertical components, we have to consider all of that. That's what we take away from this problem. So I look at all the components in this direction, here, or opposite. Now, what would happen if we did this same problem and we added a friction surface, right? So where now we have some type of friction going this way. This is actually a good question. How would this affect the problem if I added friction? How would this affect the problem if I added friction? If I change the surface to be a friction instead of frictionless?
You would have a force on that possibly make it unbalanced.
Yes, unbalanced. Would that affect the normal force though?
That wouldn't affect.
No, because the individual components, horizontal and vertical, are what? P word?
Perpendicular.
Perpendicular, which means they are
Independent.
of each other, independent of each other. Make sense? All right. Now, why did I give you that one? Go to this next one, right? Make sense? Yes. 75. We're good. This one right here. Now that we just did this, right? If your brains are fried, I understand, but we actually are making good progress right now. So, like, I'm going to just
My brains are fried.
I know. I'm going to keep pushing only because this is actually, you just need this, right? We're going to see the problem that we actually do. The problem that you do that's going to be on the final exam is actually very easy. But I have to give you this because this is friction surfaces. Like, you need this. All right, so we here. Now, how do we go about this problem right here? The first thing I want us to see, right? It tells us what? A box is being, we want to just find the offensive values, right? But let's read this. A box is being pulled at a constant speed of 0.4 meters per second across a frictional surface. Perform an extensive force analysis of the diagram and fill in the blanks. What is the main thing that we just said in this problem?
I honestly don't even know.
One more time.
It's a constant speed.
There we go. A box is pulled at a constant speed of 0.4 meters per second across a frictional surface. What does that mean if it's pulled at a constant speed?
No acceleration.
No acceleration. So therefore, if there's no acceleration, then are the forces balanced or unbalanced?
There's no force.
Hold on. There's force present, but what is it? The forces are what? Balance. There's no acceleration, but there's force. So now we know that the forces are balanced. So therefore, the forces are balanced. Which equation of Newton's laws are we going to use? First law or second law? First law. The sum of the forces equal balance. So now we can actually let's do two of these, right? Because we need to know the forces that are balanced in my X and the forces that are balanced in my Y, because I have two types of components, right? So let me redo this free body diagram. I'm here, it has a weight, because it's a big old box, right? Going against the surface. Normal force. And a little bit of friction. Going this way. Applied force going up. That should be it, right? Yep. The applied force, I don't know why I just don't put this in my hand. This is 38 newtons. No, it's not. This is 80 newtons. Sorry, I got the wrong problem. And we want to find everything else. The only thing they give us is this, the angle. Oh, they tell us this is kilograms. All right. And I'll give you one more. Frictional force is equal to no. The coefficient of friction is equal to a normal force divided by frictional force. I believe that's right.
Isn't it friction divided by normal?
Letting me guessing.
It's friction over normal.
I bet you it is, because I know I'm probably wrong. How do I do this? Just so I can have it, so it can be on a recording. Yep, there we go. Right there. And I can actually write it like that. Mu times the normal force. Yeah, I was off. Let's see. See, I just gave you a nice little review when you go into recording. And even just looking how I'm going through these slides, look how much information we've covered this semester. Isn't this wonderful? All right, right here. Mu times the normal force, right? So we got our X and our Y. So basically, all these are going to be balanced to where my left equals my right and my up equals my down. So let me represent these even with the components, right? I know that this is going to have F applied, and this is going to have F applied Y, X, Y, right? So that means my left must equal my right. So that means my F applied X, because this is in equilibrium, there's no acceleration, must equal my frictional force. Then if I do my up and my down, right? Let me list all the up ones, right? On the bottom, I have gravity. And then I have F norm plus the F applied, Y. So let's see how I can find all of these. Now, real quick, let's do an easy one. Which force can we find real quick? Gravity, right? This is equal to mass times acceleration due to gravity, which is 20 kilograms times 9.8. What's 20 times 9.8?
196.
196. Now we know that F gravity is equal to 196 newtons. Plus F norm, and then right here, F applied Y, right? Well, real quick, let's look at this. What is this? Does it look familiar?
45, 45, 90.
45, 45, 90. Good. You rewrite this? 45, 45, 90. This means my sides are the same. So if I just find one, I should be good. So that really means this is X, and this is X root 3. Sorry, root 2. This is equal to 90. So this means this is 80. Sorry, this is equal to 80. So for me to find X, I basically have to do this, right? I want to find out what X, so I have to divide by root 2. 80 divided by root 2 is how much?
56.6.
56.6. So now I know that both of these are 56.6. 56.6. So that can come down here, 56.6, 56.6. So now I have my vertical component. So now I know my frictional force must be equal to 56.6. And I have my F applied as 56.6 newtons. Now I know what my frictional force is. It's 56.6 newtons. And now because I know that, I can figure out what my normal force is. I see addition, so I must do subtraction. So let me subtract 56.6. I take that away from 196. And I should get what for my F norm?
139.4.
139.4 newtons. So now that's my F norm, right? Now I can figure out my coefficient of friction, right? Because I know that my friction is 56.6 newtons. And then my F normal force is 139.6. So now I divide 139.6 divided by 56.6. Sorry, 139.4. What is 56.6 divided by 139.4?
0.41.
0.41 is my coefficient of friction. Yep. The biggest thing to put with all of those together, right? Yes, we just did a lot of math, but it's still the same process. I took the free body diagram. I found out one, just from the notes they're telling us here, is constant speed. So now I know there's no acceleration. When we know there's no acceleration, now I understand, okay, no acceleration. That means that all my forces are balanced. So what equation am I using? The sum of my forces is equal to 0. So now when we knowing that, now I take that, right? And I apply it everywhere else. So now I just got to find my pairs. You know, my left is equal to my right. I can find my right. It's just this 45, 45, 90 triangle. Let me pull it out and find these values. So now I put that here. Okay, I found my right. That's equal to my frictional force now. Boom, found that one. Now I need my vertical force because I need to find that one compared to that. Oh, we also found gravity first, force due to gravity, which is weight. So that's here. Mass times acceleration due to gravity, 196. So now I'm here, right? Add that together. Now I can just take that same applied force, my y that I found, subtract that. Now I find my normal force. Now once I find my normal force, I can use that to find my coefficient due friction. So we're there. Yes.
Are you gonna, be available to office hours?
I'll make myself available. Yes.
I don't know where you can on office hours, but I haven't tried it yet.
It's been tough, but I will make it work. So that's what we have so far for that one, right? That one was just to kind of show you how you put it all together, but it's still the same thing of using these vector components, looking at forces in the different components, and then just playing around with the stuff that we have here. So this one did take and put together everything that we've pretty much done in the last like 4 units. You too. Now, this is a part I believe I can walk you down in this one. I can try to do this in like 25 minutes. And the reason why I want to do this one together so that you can get it, but I don't ask a question about this on the final exam, but you do need it. Were my answers right? Before were they checked? Were they right? I mean, I just erased it, but.
I think so.
Okay. So now on this, right? That was on a level surface. Now let's talk about slants, right? So when we have a slant, right, the normal force is always parallel to the surface of the object. Sorry, the surface that the object is tapped on. That's always a normal force. So if we look on like a flat surface, like this table, the normal force is, doesn't say parallel. I meant to say perpendicular. It's perpendicular to the surface. So the normal force is perpendicular. So that means if I have a flat surface, it's perpendicular, so it's just straight up, right? So if you were to think about it, right, flat surface, normal force perpendicular. If I just slant it, right, where would my normal force be? Kind of like on a tilt, right? But if I have it straight here, box, surface, we got gravity here. What's the gravity? Normal force. We want to announce if I slant the surface now and I have my box here. Now think about it. What direction is gravity going to always be? Down. Gravity will always still be this way, right? Now, what direction would a normal force be? Slight little slant. Right? And let's just imagine this is a surface with friction. What force would we see like here, right? If we had it and it was going this way, right? What force would you see going this way?
That's friction.
That's the friction, right? How would it look on the slant?
Be parallel to your
What is that?
This is slanted out.
Slant it up. Which way would it go? This way or this way? Like this? That match what you see in the diagram? So that's how we look at the free body diagram and the forces of an object on a slant. It's still similar to here, but literally, just think about, you just turn it. Gravity will always be directly straight down towards the center of the earth. The other forces, we just tilted it. So now we got the friction going behind it, normal force coming at an angle. Why is that important? Now, we can start looking at how we can talk about the perpendicular and parallel forces, right? So this helps us to do some analysis when we have it on a slant, right? So let's keep this diagram, right? I can now take what I have and create a force called the perpendicular force, which is really equal to the normal force, right? Let me call this the perpendicular force, right? Then I can make that come across and be equal to a force that I call parallel force. Right? Which is parallel to the surface. Perpendicular force is perpendicular to the surface. Parallel force is parallel to the surface. So now I have a what? What is that? A right what? Triangle. So I could pull this out. Now I'm here. My hypotenuse is gravity. The angle in between them, that represents perpendicular force, and then we got the normal force. What we want to do right now is just do some quick trig to be able to find these components, right? So let me just do some quick trig. Remember, bring it back.
Would it always be the force of gravity that's the like the hypotenuse?
Yes, so it's always going to be down. So in
Okay.
this scenario, when we're using these, it's always going to be gravity, yes. So now we come here, right? Which one would I use to find my my perpendicular force?
Sine?
Sine, cosine, you said sine, right? Yep. So I would say sine of my angle is equal to opposite of hypotenuse. Now, real quick, F gravity, right, is equal to what? The what?
Mass times acceleration due to
Mass times the acceleration due to gravity. So F grav is equal to M times G, right? That look familiar? So now I can put M times G right here, right? So now when I do this, why does that matter? Because when I get here, sine of my angle, whatever my angle is equal to opposite F parallel times my hypotenuse. Mass times gravity, right? Let me use the black so you see it. Mass times gravity. So if I want to find out what my perpendicular force is, all I have to do is multiply mass times gravity. So now I have mass times gravity times the sine of an angle is equal to my perpendicular force. So now I have an equation for that one, right? My perpendicular force is equal to mass times gravity times the sine of my equation. Take a wild guess what the parallel force will be. If you had to come up with an equation for the parallel force. Actually take a wild guess. Don't compute it.
Same.
Jerry says the same.
Wait, wouldn't the perpendicular be cos actually? And the other one be sine?
Oh yeah, I switched the angle. I put the angle at the wrong. I was looking at the wrong one. One more time. The angle really is here.
Because the parallel side would be opposite the angle, right?
Hold on. Parallel is opposite. This makes sense. All I'm gonna do is switch this. Still same thing. Now this is opposite. So now, all right. Still same thing. Carrie says it's still this one. Let's do it one more time. Let's actually prove it. So now I'm gonna come over here, right? I want to find out this one. Which equation would I use? Sine, cosine, or tangent? I want to find this one.
Sine?
For perpendicular. Remember?
Oh, cos.
Opposite, adjacent, hypotenuse. So this one's cosine. Cosine of the angle is equal to adjacent times hypotenuse. Adjacent, F perpendicular. This is mass times this, cosine of the angle. Multiplied by here, here. So all we change with this one, cosine.
So will this always be the case where the perpendicular is a cos and the other one's a sine?
Exactly.
Okay. There is a C in perpendicular. To remember.
There you go. That's what you can remember. But this is to help you out with the slant. So when we get to a problem, you have this, right? But this, all you did was, and they even set it up for us, is just pull the triangle out and it gets you able to figure out these two equations. So now I did it for you. Now, when you go back and do your practice problems, actually try and do this again, do the whole tan sine calculation just so you can get it. But this is what they were looking for. And we use that because now we can use that to kind of do some intuitive analysis, right? See, I told you I'm making good time. You're almost done. Well, yeah. So now let's look at this, right? And let's try and evaluate each one of these situations using the less than, greater than, equal than sign, right? So let's literally not do any math, and let's go ahead and just look at it. So for these three situations, right? For the first one, right? The object is at rest. So how can we compare the parallel force compared to the frictional force? Is it greater than, less than, or equal to if the object is at rest? I got one for equal to. What about the frictional force? Sorry, the normal force and the perpendicular force. Greater, less than, or equal to?
Equal.
Equal. Okay, that makes sense. Because if they're at rest, then that means that the forces would be, some of the forces would be equal to what? 0. All right. Now, if the object moves at a constant speed, are some of the forces going to be greater than, equal than, or some of the forces going to be unbalanced or balanced? Balanced. So then the sum of the forces should be what? Greater than, less than, or equal to? Equal, right? So yeah, if it's at constant speed, that also means that it stays equilibrium. So the sum of the forces is equal to 0. So both situations should be equal to. Now let's think about this, right? The object accelerates down on an incline. Is the parallel force going to be greater than, less than, or equal to the frictional force? Greater than. Why would you say greater than? Because it's accelerating. Which way is it going? Downhill. So which one is technically winning? The parallel force or the frictional force? Parallel, winner minus loser, right? Now this one, be careful. The perpendicular force, is it greater than, less than, or equal to the normal force?
Isn't that equal?
Yes. Why do you say equal?
Because there's no acceleration up or down.
There's no acceleration up or down. So therefore, does the object stay on the surface or leave the surface?
Stays on it.
Stay on the surface. Does that make sense? See the answers? Those last three problems that we just did was all conceptual just to help you understand the incline. Why? Because now we can do one problem, right? Now we're just doing the same thing. We want to just use trig functions and Newton's laws to fill in the blanks. So let me redraw it. We got the object of the sun. Which one is this? Is this the first one? Yeah. an object on the slant here. It's a lot of lines, right? But we got our normal force over here, frictional force over here, F parallel, F perpendicular, and then force due to gravity here. Right? Now let's put this all together and start filling in the blanks, right? Now, what them telling us, this object is accelerating down an inclined plane at 36 degrees with the horizon. It has a coefficient of friction of 0.54, 0.548. Friction, one more time, times a normal force. So understanding that, right? The object acceleration. So are my forces balanced or unbalanced? Unbalanced. We do have some exponents and y exponents, so we want to look at both situations, right? So we got some where the forces are balanced, and we got some when the forces are unbalanced. So if it's going down the incline, we just did this. Okay, this makes sense now. We just did this, right? It's going down, accelerating down. Which forces are unbalanced? Friction and parallel. So let me say it in a better way, right? Instead of me saying left and right, I could say uphill. I still have here. So if it's unbalanced, that means here I have a winner and a loser, right? Which one is winning? Which one's losing? Uphill or downhill? Downhill. So now I have my winner minus loser. Downhill is beating my uphill. That's equal to mass times acceleration. What force is downhill? What force is uphill?
Friction.
And that's equal to my mass. Now, what we just established earlier, right? There are some forces to where the sum of the forces is equal to 0, right? Where they're balanced. Where was our forces balanced in the previous problem? In all the scenarios.
The perpendicular.
The perpendicular and the normal force, right?
Mm-hmm.
Will anything be different in this scenario? Would the perpendicular be equal to the normal force?
Yes.
Yes. So now we know that we have the perpendicular force is actually equal to the normal force. Now, why does these things matter, right? We can actually calculate this because what do we have before, right? Remember these equations we just came up with? Correct? We just came up with these equations. Now we can actually put this in for this. So our normal force is equal to mass times gravity times the cosine of the angle. And our parallel force minus the frictional force, now we have mass times sine times the angle minus the frictional force equals mass times acceleration. Now the first thing we could do is we know the mass right? We know the mass, we know gravity, which is 9.8, and do we have an angle? Yes. So can we find out the parallel force? Yes. Let's find the perpendicular force. The mass is 4.5, right?
Yes.
4.5 times gravity, 9.8, times cosine of the angle is 36.
Yes.
You put all that together, and what value do we get? Sorry, I'm tripping. Cosine of 36 times 9.8 times 4.5. Did you get 35.6?
Yes.
Then we're going to just do the same thing for a parallel force, but just change the sign. Did you get 25.9?
Yes.
There we go. So now we got these two values, right? 35.6 newtons. And that's actually going to also be equal to our normal force. So now we can write our normal force, 35.6 over here. Then we have 25.9 minus the frictional force, which is equal to our mass, which is 4.5, times our acceleration. We don't know the acceleration, we don't know the frictional force, but can we find it? Let's look, right? We know that the frictional force is, hold on, we have mu, right? They gave us mu, right? 0.548, right? So now we have mu and we have the normal force. So now can we find the frictional force? So let's do that. We got the frictional force, which is equal to mu 0.548 times the normal force, which is 35.6. So now the frictional force is equal to
19.4.
19.5. So now we come over here and we can plug this in for the frictional force. Now we have a true winner minus loser situation, right? 25.9 minus 19.6, which is how much? Should be like 6 something, right? 6.3?
Yes.
6.3 newtons equals 4.5. I see multiplication. So now I do division by 4.5. I divide each side by 4.5. 6.3 divided by 4.5. My acceleration is equal to what?
1.4.
1.4 meters per second squared. Did I hit everything?
Yeah, I have a question.
Go ahead.
My brain is turning into spaghetti noodles. Do we have to go another 30 minutes?
Y'all, I'm finishing this. The only reason because like I want to make sure that we do this so we done with this. You'll see how let me finish this. Because once we done with this, y'all done with this unit, and I can move on, and I'll make sure I slow down. But yeah, I'm about to finish this.
Okay.
And then I think we got it, the net force right here. The most important things, knowing when to use Newton's law, first law, second law, right? And which scenarios, right? Coming back from this one. The normal force is always equal to the perpendicular force right here, right? In these situations, especially when it's touching the surface. So in that scenario, we will be using first law, right? But like in this one, where you see accelerates down the incline, that's when we see we have winner minus loser situation. So then we have to look at the some of the forces being equal to mass times acceleration. That's what we have over here on the right. But we use those equations that we developed here in the beginning to help us be able to find that very easily when we're dealing with stuff on the downhill. So we just did that one, right? Now this one. This one should take 2 seconds. And why it should take 2 seconds is because I want you to think intuitively. Look at it before I start reading it. While I erase it, the board, it's the same type of problem. But this one shouldn't take as much math. Yep. A 65 kilogram crate remains at rest on an inclined plane that is inclined at 23 degrees with the horizon. Now, with hearing that, it's at rest. What does it mean when it's at rest? What does that sound like? What does that sound like on my forces? My forces are balanced or unbalanced? If it's at rest.
Unbalanced.
Balance. If it's at rest. Balance. Not moving. Sorry. Ooh, I shouldn't have said that. It's at rest. It's at rest. Now with it being at rest, right? Some of the forces are equal to what? 0. Balance. Some of the forces equal to 0. So now we over here, right? We don't even got to look at this one. Balance. So now what does that mean, balance? Let's start with our first scenario, right? We did it last time. We had normal force is equal to the perpendicular force. And we also have my uphill is equal to my downhill. So this part equal to here. What does that mean? That means my F parallel is equal to my frictional force. Now, what can we do? Remember, we have these two equations that we already figured out. Right? They told us that this angle that it's slanted at is 23 degrees. So it's over here, but that means it's also right here, right? We also know our frictional force is equal to mu times the normal force. Now, when I have this, right, remember how I had my triangle and I was able to pull it out? Let me pull that out over here. This is 23 degrees. Now I'm here. Gravity, right? What is my gravity? We got 23 degrees, 65. This is my gravity, right? The mass is here. So now we got 65 times 9.8. What's 65 times 9.8?
637.
637. I thought it was gonna be nice. Yeah, we're gonna do a little bit. All right, so we got 637. That's fine. 37 times the cosine of the angle, 23. And the sine of the angle. That'll help us find our normal force, sorry, perpendicular force, and our parallel force. See you later. $586. That was cosine.
$249.
249. 249 here, right? So now we have these two, right? So now I know that my frictional force is equal to my parallel force, which is 249 that I just found right here. And my parallel force, my perpendicular force is equal to my normal force. That's 586. 586 newtons. Frictional force, 249 newtons, right? Now the only thing other thing I have to find is my coefficient to friction, which is mu. So now I come over here. I know this is 586 for my normal force, sorry. My frictional force is 249. This is 586. And I just divide. So then my mu is equal to
0.425.
0.425. And just thinking about it, my net force is equal to what?
Zero.
0. So therefore my acceleration is equal to also
Zero.
0. You could have went backwards and started with net force equals 0 and your acceleration is 0, went from there. But this is pretty much just the same thing. But now instead of we having this winner minus loser, we just set everything to be equal to each other and use pretty much these two equations. So this is plane analysis. That was literally everything thrown together. So that one was probably the hardest part. With your brains fried, now we are at the end. This one, way easier than any of the ones we just did so far. This is the problem that is on your final exam. Suppose that a student pulls with two large forces in order to lift a 1 kilogram book by 2 cables. If the cables make a 1 degree angle with the horizon, then what is the tension in the cable? This is similar to actually the problem that we started off today, the sine problem, right? You have something hanging in the middle and it has a weight that goes down, right? And you have two string cables, whatever you want to call it, that have tension, right? This problem is the same as that one. Because how did we solve it? That one? We represented the vertical force and the horizontal. X, Y, and the angle in between. So then when we came over here, we know we in a state of equilibrium. The sum of the forces is equal to 0 because they're balanced. And we know that was in the Y, right? So now we say F up equals down. So FTY plus FTY is equal to my gravity. Two of them, so let me add them together. Divide by 2. So my Y component for my tension is equal to my F gravity divided by 2, which is really a mass times gravity divided by 2. And then this right here, we could pull out to be its own individual triangle, right? So now we have the tension angle equal to mass times gravity divided by 2, because that's what FTY is. And then whatever this X component is. But we're not really too much worried about the X component. We really just want to find out what this Y component is. And usually they're going to give us this. So let's come back over here, right? We have that same arrangement, right? They tell us to lift a 1 kilogram book by 2 cables. So now we know that the mass is actually equal to 1. So with the mass being equal to 1, we could put 1 right here. Multiply that by 9.8 meters per second squared, because that's what we know gravity is equal to, right? What's 1 times 9.8? 9.8. So now we got 9.8 over 2. What's 9.8 over 2?
4.9.
4.9. So now I know that this FTY, all of this over here, right, is really equal to 4.9. So now all I have to do is use one of my trig functions to find out what my hypotenuse or tension is, right? Which trig function would I use? Sine. Because my angle is how much?
1.
1. So now I come over here, sine of the angle is equal to opposite over hypotenuse. Sine of 1 is equal to opposite, which is 4.9 over my hypotenuse, which is my tension. Do a little bit of manipulation. I'm gonna multiply both sides by FT. FT. So now I have sine of 1 is equal to 4.9. I see multiplication by sine of the angle. So I divide by sine of the angle. So literally just divide sine of 1 by 4.9 divided by sine by 1. Sine by 1. And you'll get the tension.
280.
280.8. So about 281. Right? So the tension in the wire is 281 newtons. I know I did that in 5 minutes because it was 8:07 when I started this problem. And why I went through it like that, we just did so many much more challenging problems than this problem right here. This is an equilibrium state. This is actually very important, especially anybody in here. Well, I don't know. But I know I had some civils in the last class, some civil engineers, equilibrium states. Honestly, anybody could use this. But I'm just saying, like this part right here, once you start really pulling out things, right? Pull out and look at the triangles to be able to pull out that trig. Understanding, really got to understand balanced forces, unbalanced forces. Which law do I use? First law, second law, and how they go in between, right? Playing around with it. It's not so much about the math, it's just knowing about how the concepts go together and then putting them together. This literally is all the units in one. That's why when I do the practice test, I want you to use all the units and put it together and take them 2, 3, and 4 so you can be able to solve these type of problems. And that's why I wanted to break it up like this. But this is the last problem, the most focused problem that I want you to get from this unit. So we got out of here. And we out of here 15 minutes earlier than I said. All right. Next unit will be momentum and collisions, but we're not starting that tonight. Pretty much that is it for tonight. I will post a recording for this right away, and I'll post the slides organized. Give me just like nothing's like it's due, but like it's not like anything's due tomorrow. Just give me a second to like change all the due dates, and I'll make sure I go over everything on Wednesday. But Wednesday we will be online at 7. So Wednesday at 7 we'll be online. So and I'll change all the due dates and have everything organized so I can give you guys updates. Let me stop the recording real quick.